Welcome to CS 1401 Video 16.1. In the last set of videos, I introduced classes and objects. In this video, I'll discuss four key characteristics of object-oriented programming: abstraction, encapsulation, inheritance, and polymorphism. In the early 1970s, the U.S. Department of Defense had computer systems that used some 450 different computer languages. The department had an IT budget that was always out of control, yet never had much to show for all that spending. The department set up a task force to look at the situation, and the task force found that 80% of the budget went to the software, with the remaining 20% to the hardware. More than 80% of the software budget went to maintenance. Only the remaining 20% went to new software development. Hardware components could be applied to various products, and their integrity normally did not affect other products. Hardware can share and reuse. Hardware faults are isolated. Software procedures were often non-shareable and not reusable. Software faults could affect other programs running in computers. The task force proposed to make software behave like hardware objects. To do this, the task force recommended that the Department of Defense replace those 450 computer languages with an object-oriented language called Ada. Let's look at four key characteristics of object-oriented programming: abstraction, encapsulation, inheritance, and polymorphism. I'll start with abstraction. Abstraction means selecting and using features that are important for solving particular problems. Objects allow us to create an abstraction of the real-life entity or event, such as a cell phone. For a class cell phone, we can create methods named dial, receive call, end call, send message, and so forth, without needing to know about the details of a cell phone circuitry. Those details are irrelevant for the purpose of showing what a cell phone can do at the level of making phone calls. That's the benefit of abstraction. It enables programmers to do things in terms that make sense for the task at hand. The second concept is encapsulation. Encapsulation is the process of protecting internal details from the outside world. Encapsulation can be adjusted by granting access rights to those internal details. Abstraction and encapsulation go hand in hand because abstraction determines what details should be visible, and encapsulation determines what the level of access rights to these visible details should be. In a sense, encapsulation implements the desired level of abstraction. In Java, encapsulation is defined through access modifiers such as public, private, and protected. Let's take a look at an example of encapsulation. In fact, let's return to the example of the class student. You'll recall that the class student was defined as public class student with instance variables string name, string email, int ID, int attendance, an array of floats called quiz, and an array of floats called midterm. When I created an instance of the class student for a student named Anna Minor, I was able to set the value of the variable name by having this line in my program: s1.name equals Anna Minor. This was possible because Java, by default, makes instance variables public. The instance variables can be accessed directly from other methods in the same Java package. In other words, my definition of the class student was basically the same as if I had written public class student and then made all the variables public by declaring them that way. But I'm not sure that I really want every method in the same package to have access to all this information. It's probably okay to let other programs know that there's a student in the CS 1401 course by the name of Anna Minor, but the other information seems like it should be kept private. Java's implementation of classes and objects let us do exactly that. We can specify that a field is private instead of public, and good programming practice is to be explicit about these choices. So here's a new version of student that makes name public and the other fields private. So far, so good. But how can we get or set values for these fields? To do so, we can create methods for this. For example, public int getAttendance returns the value of attendance, even though attendance is an instance variable that's private. Similarly, public int setAttendance sets the value of attendance to its argument, even though attendance is a private instance variable. In general, authors of classes provide set and get methods for variables to which the authors wish to provide access. Here's another example, this time involving money. Let's say we are managing a bank with some accounts. We have a class named bank account. Each customer in the bank has a bank account object. In the bank account object, the account name, number, and balance are all kept private. In other words, these variables cannot be accessed from outside of this class. For example, because balance is private, we cannot assign an amount to a balance by just writing hsimpson.balanced equals 10,000, as much as H. Simpson would like to have that 10,000 in his account. To give accessibility to these fields, we can create three get methods: get account name, get account number, and get balance. Within these methods, we can create conditions to limit unauthorized access to the object's data fields. For example, we have methods to deposit and withdraw money. The withdraw method should make sure that a customer cannot withdraw more than the balance. One of the benefits of encapsulation is that it enables us to modify our code without breaking the code of others who use our code. The third characteristic of object-oriented program is inheritance. Inheritance is the process of creating new classes that build on the fields and methods of existing classes. The new classes will automatically inherit all the data fields and methods of the original class. And on top of these fields and methods, we can add more fields and methods in the inherited class. For example, let's go back to the class bank account. It turns out that bank accounts can be of two types: savings or checking. A savings account adds interest to the account balance. Interest is calculated and added to the balance periodically. In a checking account, there is no interest, but there may be a transaction fee after a certain number of free transactions. One way to deal with this new situation would be to copy the class bank account and to create two new classes with the same code while adding additional fields and methods. A major disadvantage of this approach is that it takes time and it creates duplicate code. Worse, when we want to update something in one class, we will have to make sure to update all the other classes. With the help of inheritance, we can extend the class bank account without copying anything from that class. At the pseudocode level, this might look like class savings account extends bank account, and then we'll add a new field, a private double, called interest rate. That's the extension. We can add methods that extend the methods for bank account so that our new extended class savings account has a method called addInterest. So it creates a double called interest, which is the balance times the interest rate, and then it deposits that interest. Here's how to do this in Java. The class savings account extends bank account. It has a private instance variable called interest rate of type double. It has a constructor that takes a string account number, a string account name, and a double for the interest rate. And its code calls the constructor for the class from which it inherits. And it does that by calling super, that's a constructor for the super class from which it inherits, with account number and account name, and then sets interest rate equal to rate. The method add interest doesn't return anything. What it does is set the variable interest to the balance times the interest rate divided by 100. That is, if the interest rate is something like 5, we really want to multiply the balance times 0.05. And then we deposit the interest. Now, I call this dot deposit, and this means I call this instance's method called deposit. As you can see from cases like this, inheritance really helps with large-scale reuse of code. The fourth characteristic is polymorphism. Polymorphism is the ability of an object to take multiple forms. That's what the word means. Poly, multiple, morph, form. In object-oriented programming, polymorphism means that subclasses of a class can define their own unique behaviors and still share some of the same functionality of the parent class. In practical terms, this means that a method from one class, for example, bank account, can be called from another, such as savings account. This is polymorphic because the method can handle calls with objects with different forms. The superclass has a single interface, a set of methods through which it can process different kinds of objects. Another way of looking at polymorphism is from the perspective of an instance of the saving account class. It can behave like a saving account object, and it can also behave like a bank account object. It can take on different roles as needed. Well, that's a look at 4 key characteristics of object-oriented programming: abstraction, encapsulation, inheritance, and polymorphism, with examples of implementation in Java. In video 17.2, I'll discuss the relationship between objects and recursion, and I'll introduce you to the linked list data structure. See you shortly.